translation roadmap. We're going to start with the relational data blueprint, move into database rules and constraints, hit our core translation mapping algebra to SQL, explore joins, and finally wrap up with triggers, views, and procedures. All right, let's just get right into it.
Section 1. The relational data blueprint. Now, before we can manipulate data, we obviously have to understand how it's structured at a foundational level.
The relational data model is absolutely the ultimate architectural blueprint for everything we build in a database management system. Proposed way back in the 70s, it basically takes absolute data chaos and standardizes it into a theoretical framework where everything is organized into tables. Just think of the table as an entity, like, say, a customer or a product. And the really brilliant part here is how this model mathematically defines the relationships between those entities. It gives us a super standardized, logical way to store information, totally freeing us from worrying about how it's physically stored on the hard drive.
Now, when we historically want to pull information from that blueprint, we look at relational calculus. And there are basically two approaches here. First, tuple calculus. This filters data by the rows, or, the tuples. You're essentially asking the system for the entire record that meets a specific condition. Domain calculus, on the other hand, well, that filters by columns, or domains. Here, you're asking for specific attributes or fields. So really, they're just two sides of the exact same mathematical coin used to query our blueprint.
Which brings us to Section 2, database rules and constraints. If the relational model is our blueprint, well, these rules are the physics that keep our whole structure from just collapsing.
Look, without rules, our relational data would turn into the Wild West pretty much overnight. That's exactly where integrity constraints come in. There are three big ones you absolutely need to know. First up, entity integrity. This basically just says every single table needs a unique identifier, a primary key, and it literally cannot be null. I mean, you can't have a nameless, faceless entity just floating around in there. Next is referential integrity. This rule dictates that foreign keys have to match primary keys in other tables. It's what prevents you from doing something silly, like linking an order to a customer ID that doesn't even exist. And finally, domain constraints. These ensure that the data you drop into a column actually matches the required data type. If a column is supposed to be a date, you can't just shove a word in there. These constraints really are the silent guardians of your data's accuracy.
All right, now for Section 3, translating algebra into SQL. This right here is the absolute core of our explainer today. This is where we bridge that gap between mathematical theory and the actual practical code you write.
So, we briefly touched on relational calculus earlier, which is declarative, right? It simply asks the database what data we want, but it doesn't really care how it gets it. Relational algebra, though, that is procedural. It gives us the step-by-step mathematical operations, the actual how to retrieve that data. So the totally crucial thing to understand here is that relational algebra acts as the direct blueprint for database engines to actually go out and execute our queries.
Honestly, this is our Rosetta Stone right here. When you sit down and write a SQL query, you are essentially just writing out relational algebra using plain English words. Let's look at the mathematical operator sigma, which is also known as selection. In algebra, sigma filters out rows based on a specific condition. In SQL, that is exactly what your where clause does. No difference. Now look at pi, or projection. In math, pi selects specific columns from a relation. In SQL, yep, that's your select statement. When you type out select name from customers where age is greater than 20, you are literally mathematically executing a projection upon a selection. It's pure algebra, just disguised as coding syntax. How cool is that?
Every single modern SQL query you write goes through this exact same life cycle. Step 1, you write the SQL. Step 2, the database engine's query optimizer takes your friendly English-like SQL and literally translates it right back into an optimized tree of relational algebra operations. And then step 3, it executes those mathematical steps, the sigmas, the pi's, the joins, to fetch your data from the tables. So you might think you're just writing SQL, but behind the scenes, your database engine is, strictly speaking, relational algebra.
Of course, we aren't just pulling data out, right? We have to put it in, we have to change it. And that's SQL data manipulation, or DML. Your insert, update, and delete operations are the commands that physically alter the state of our blueprint. But remember, even these operations are totally bound by the mathematical rules we talked about earlier. Try to insert a record that violates an entity integrity constraint, and boom, the database's mathematical logic is going to reject it immediately.
Okay, let's step up the complexity a bit. Section 4, joins in complex queries. This is where we mathematically combine data across multiple different tables.
Now, in relational algebra, a join is technically a Cartesian product followed by a selection criterion. I know, that sounds super intimidating, but it literally just means mashing two tables together and then filtering for the spots where they match. Think about an inner join as a strict intersection. It only returns the records that have matching values in both tables. But an outer join, that's a bit more inclusive. It combines the intersecting records, but also keeps the unmatched records hanging around from one or both of those original tables. At the end of the day, it is all just set theory.
And the wild thing is, we can stack these mathematical operations to absolutely incredible heights. When you're using queries, subqueries, and aggregate functions, things like sum, AVG, or count, you are actually building these dense layers of algebraic combinations. Think of a subquery as just an algebraic operation nested inside of another one. The engine goes in, resolves the innermost math problem first, grabs that result set, and basically feeds it right into the outer math problem. It is incredibly elegant when you start viewing it through that lens of mathematics.
Finally, let's look at Section 5, Triggers, Views, and Procedures. This is the heady machinery. We're talking advanced database automation here.
So let's kick this off with views. A view is basically a virtual table based on the saved result set of an underlying SQL statement. Try thinking about this in terms of everything we've just learned so far. A view is really just a saved, highly complex algebraic formula. So instead of running out some massive query with a dozen joins, sigmas, and pi's every single time you need it, you just save that algebraic tree as a view. Then you can query that view as if it were a real physical entity right there in your blueprint. It just beautifully simplifies complex data retrieval.
And to make our database truly robust, we rely on advanced automation tools. Let's talk about indexes for a second. If you've ever felt the absolute sheer agony of waiting for a database to scan every single row of a massive table, then you already know exactly why indexes matter. They create specialized data structures, like B-trees, to drastically speed up those mathematical search times. Then we've got triggers. These are automated actions that instantly fire off the second a specific mathematical operation happens. And then procedures. Using extensions like PL/SQL, procedures let us write really complex programmatic logic that lives right inside the database itself. It completely turns our static blueprint into a fully automated machine. Okay, so here is the biggest takeaway you really should grab from today's explainer. Understanding the underlying math fundamentally makes you a better SQL programmer. Honestly, this is why all of this stuff matters. When you realize that your where clause is actually a mathematical selection and that your database engine is constantly optimizing this massive tree of algebraic formulas, you stop guessing. You start architecting queries that work with the database's physics instead of fighting against them. You elevate yourself from someone who just types code to someone who is truly engineering data. So, I'll leave you with this. If relational algebra is the hidden language powering literally everything you do with data, what other secrets is your database hiding in plain sight? I highly encourage you to look at your next complex SQL query, not just as a block of text, but as a beautiful, intricate mathematical equation. Thanks so much for joining me on this explainer, and keep exploring.